Hello, it's Keith here, and this is lesson 8 of the Photon series, Photon being my little Tron clone. You can see it here, and today we're going to be looking at the PC Engine, which is one of my favourite 6502 systems. You can see the game here. It's a very simple little Tron game. We have to try and get our enemy to collide with our line. The game has a boost mode where you can move faster. I've just run out. And the other thing that's worth noticing, when you press a direction button, if you press it, you have to release before you can press and turn again. And that's going to be important because we're going to see it later in the code. Now, what I personally think is quite fun about this game is it's a pixel-based game. The title screen and the fonts are drawn in pixels of vectors. And this is a tile sprite-based system. So we're basically looking at every single system and trying to work out a way in which we can use it like a pixel-based system, even though it's a tile sprite one. And so that's what we're going to be looking at today. Okay, well, we're going to go over to the source code and we're going to have a look. Okay, so here is the start of the game code. Now, every version needs some settings defined. There's some memory for the game variables, and we also have to define the screen size. Now, screen width 32 basically defines that it's a full width screen. Some of the systems have very small screens. We need to scale things down, but not for this one. And we've got the width as 256 and the height as a slightly strange 224. Because this is a vector-based game, everything's drawn in dots and lines and things, and we can very easily manipulate it to work with different screen sizes, so that's what we've done here. So we've got the full range being used. Now, this system is a 16 colour system, but the game can actually only use 5 colours, colours 0 to 4. So we're using all of them. Some systems we've only got 3 colours, so we have to remap one, but not this system. And then we've got some initialization. Now, we're not going to cover everything in today's example. A lot of the code here is copied from YQuest and even the simple series. Things like reading the joystick, setting up tiles. We're not going to be discussing that kind of thing here, just the new stuff with regards to plotting pixels within patterns of tile definitions. So here we've just got setting up the hardware, the memory here, setting up the screen, resetting the scroll, and here we're loading in the palette. So that's getting things ready. Now this is where we're going to start looking at the interesting stuff. What we're doing here is we're using the fill area with tiles command, which was from the simple series, and we're basically filling the entire visible screen area with tiles that are consecutively numbered. Now if they were numbered from 0, there would be 0, 1, 2, 3 all the way up to 31 and then 32 and onwards. But they're actually starting from 256 on the system. Now the PC Engine is a little bit confusing if you're getting started with it. Confused the bejeepers out of me. The memory for the pattern definitions and the memory for the tile map are actually the same memory. So tile 0 is actually used by the tile map definition, and you can't define a pattern for it, or you corrupt a tile map and you can't define a tile in that position, or you corrupt the pattern map. So we're starting from pattern 256, so that's the first tile number. And that is memory address in VRAM 1000 onwards. So those are the memory addresses that we're going to need to change the visible pixels of the screen. So that's setting up our screen with consecutive tiles, and then we will alter those tile patterns to make pixels that appear and disappear. We're wiping our memory for our game here, and then we're loading the main menu here. Now this is the start of the main game loop. We're going to discuss the pixel plotting in a moment. So first we're checking the tick number. Now the tick alternates between 0 and 1, and this is for that boost mode I mentioned. If the boost mode's set, then we draw an update for the player every single tick, otherwise it's every other tick. So that's what happens there. Now there's a pause in between each update. The pause is lower for the boost mode, and that's not really to increase the speed of the game. It's actually to compensate for the redrawing of the font in the corner, because the font routines aren't fast, but they are multi-platform. They're very compatible for other systems, so it's a trade-off. I did want this to be entirely pixel-based and not use any raster graphics though, so that's why I'm using that slightly slow font there. Then we're setting up D to be our storage for any directions that are pressed, and we're looping here and we're checking if the player is currently holding any buttons down. If they're not, then we're clearing the timeout, and that's to stop multiple key presses being detected unless it's been released first. We're going to see that in a moment, and then we're just looping until the delay counter reaches 0 here. Okay. Next, what we're doing is we're checking if the key timeout is 0, and if it's not, then the player has never released the key. So we're not going to process any key presses this time. Then we're clearing the boost counter. We'll set that later if the fire button is held down, and we're going to check the directions. Now, set player direction will turn the player. The player moves in 90-degree increments north, south, east, and west. And to use this, set player direction will alter the memory address pointed to by 0 page entry marked IX. So we're setting that to the player acceleration here. This can work with the CPU directions as well, you see. So we're setting that there. We're then decreasing or increasing the player direction if the player's turned left or right, and updating the variables with that set player direction function, which is in the multi-platform code, which is where it should be. Now, what we're doing here is we're checking if the fire button is pressed. If the fire button is pressed, then we are checking the boost power, and if the boost power is not 0, we're turning boost on by writing a 0. Now, I should have also mentioned, if the direction keys are pressed, we're setting a timeout here, but we're not setting one for fire because the fire button can be held down. Okay, and then finally, we're updating the player and the CPU. That the player will deal with that boost power and also, of course, the collision detection and good stuff like that. And finally, we're just looping back to the top. And this is the entire main loop. It's very, very short, and that's what it should be. We want as much code as possible to be multi-platform. And that's how I can port this to a different system pretty much every day. It took only a few hours in a lot of cases to port this to a new system. All I needed to do is replace the joystick code, make a few changes to the speed and things maybe, and do the PSET routine. Very quick. The game I'm currently writing, the Suck Hunt game, which is a stereoscopic shooter. The graphics routines are a bit of a nightmare, and that is taking more like a week to port. And that's a problem. There's a lot of different graphics routines in that one, and they're very platform specific, and it's a bit difficult. So as I say, the more code that's multi-platform, the faster we can port to new systems. So that's why, as I said, we really want to keep it all out there in the multi-platform. Here's the full area with tiles routine. This is the same as before. We're just consecutively filling the tile map, and the tile map is at 0, as I said, in memory. And this is the interesting bit, the PSET command, which is to set a pixel. Now, some of the systems are able to go over 256 in the x-axis, so we're using 2 register entries here. We're using the accumulator and 0 page entry B as the x-coordinate in theory. In practice, though, we're not actually using the accumulator on this system. So ZB, 0 page entry B, and ZC are the XY axis. 0 page entry D is the color. We're defining those within a fake 0 page. I tend to work in the same way as the Z80 because this game was ported from the Z80, so that's why I do that. I know some people might not like that, but that's what I do. Now, each tile on the screen is going to be 8 by 8, and each byte within that tile is going to be a bit plane, and so it's going to contain 8 pixels in total. So what we're going to need to do is we're going to need to work out which bit within that byte of the bit plane we need to change for our relative pixel. So what we're doing here is we're taking the bottom 3 bits of the x-axis, that's going to be 0 to 7, and we're looking them up in a pixel mask, and you can see it just here, and this is going to convert that 0 to 7 to be a pixel position within the byte. So that's going to be our mask for changing the bit plane. So we're getting that in there, and we're pushing it into the accumulator for later. And then what we're doing next is we're using the calc VRAM address function. This will change 0 page entry HL, ZHL, and that will change it to the memory address in VRAM of the line of the pattern that we have got visible on the screen within that XY coordinate. So it's going to take that XY coordinate and convert it to a memory address, and then we're going to need to change the pixel data of that memory address, and that's what we're doing here. So we're selecting the VRAM memory address here using these ports here, and then we're reading in 2 bytes. Now, the way that this system works, basically the first 2 bit planes are separate to the second 2. So we're loading in the first 2 here, we've got 2 bytes there, and then we're resetting the VRAM address for writing this time, and we're going to change those 2 bit planes depending on the color we want to write in D. Now what we do is we get back that value we calculated before here, that bit pixel position here. We store that in ZB, and that is going to be the mask for the pixel we want to change. We then flip the bits and store that in C. That's going to be the mask for the pixels we want to keep, because there's 7 pixels we don't want to change and 1 pixel we do. Then we're checking the color that we want to set, and we're rotating 1 bit out, and that's going to be relative to the bit plane that we're looking at. So we're looking at bit 0 here for bit plane 0, and if that bit is a 1, then we want to OR in the mask for the pixel we want to change, and if it's a 0, we don't want to, and we just want to remove that pixel, the bit for that pixel, from the value that we write back, and that's what we're doing there. So that's bit plane 0. We then do the same for bit plane 1. Now next what we do is we alter our HL address and we effectively add 8 to it, and that's because there are 8 words from the first 2-bit planes to the second 2-bit planes, so 8 memory addresses in HL. So we're incrementing HL by 8, and we then write that new memory address to the reading registers here. We read in another 2-bit planes, bit plane 2 and 3 this time, and then we set the address for writing, and we're going to do then the exact same as we did for bit plane 0 and 1 for bit planes 2 and 3. Check another 2 bits out of ZD here and set the bits in the destination, writing them back accordingly, and that means we've changed all 4-bit planes of the memory address for the pixel we wanted to mess with, and that has set our colors. Now if you only wanted to do colors 0 to 3, you could skip this second part, but this version does allow us to do the full 16 colors. So that's setting a pixel, and the point routine is almost the same. We're getting the mask again, calculating the VRAM address, reading in 2-bit planes, and this time we're just testing the pixel that we want to look at and setting the carry and rotating it into ZD accordingly for all 4-bit planes, and then just rotating right 4 times to move from the top nibble to the bottom nibble, and that should give us a color from 0 to 15, representing the pixel that was read in. Now I do have to point out this game Photon doesn't look at the color number, it just looks at black or not black, and anything that's not black will kill you. So very simple there, but in theory it is reading in all the colors. Okay, so obviously a lot of the work here is being done by the calc VRAM address, and we're going to look at that now. So we need to understand the pixel format within VRAM for the pattern data. Now as I say, there's 8 horizontal pixels in each byte, so we're ignoring the bottom 3 bits here, and we're just taking these ones. Now there are 8 lines per pattern, and there are 2 words per line of that pattern, so we're multiplying these bits by 16, and that's going to get us the relative tile across the screen for the one that contains our pixel. So we're doing that multiplication there, effectively multiplying the value in these bits by 16 here, just with 1 shift to the left, because this is the bit 8 position, and then we are storing that, and then what we're doing is we are taking these 3 bits here. Now these are the bottom 3 bits of the Y coordinate. Now these are going to be 0 to 7. As I say, there's 8 lines per pattern, so we're just taking those and storing those as is, because that's the position down the screen. As I say, there's 2 bytes per line, but we're actually working in words here. The VRAM addresses are in words, so we don't need to multiply that up, and we're storing that as well. We're then taking these remaining bits here and we're multiplying them by 8, because there's 8 lines per pattern, times 2, because there's 2 sets of data. The first is bit plane 0 and 1, and the second is 2 and 3. So we're multiplying that by 2 for that. And then we're multiplying by 32 because there's 32 tiles across the screen. So effectively we're working out based on the strip of the screen, each strip being 8 lines tall, and we're multiplying that up to work out the memory address relative to that, and we're adding that as well to our calculation. Our patterns base is a hexadecimal 1000, so we're adding that as well, and this all together is giving us our VRAM address for the pixel of the tile that we want to change relative to the screen, and that's all that's new. The rest here, this is all the same as it was in the Simple series, so and also YQuest. So if you want to see how that kind of stuff works, please see the Simple series bitmap drawing example or the YQuest game. The final thing to look at, I guess, is the clear screen routine. We're clearing from memory address 1000. We're clearing hexadecimal 4000 bytes, and we're just writing consecutive zeros to memory, just wiping out all of the pattern data there. That's our clear screen routine, very simple. And there we go. So that's all we're covering today. As I say, the Photon game is not the most amazing game in the world. I'm not pretending it is, but I think it was a nice, simple game. I think it's the kind of thing, as I say a few times, that you need if you're starting up writing your own little games. You need to start simple and aim for realistic. You don't want to aim for the moon and end up with nothing and feel disappointed. So I think a little game like this is a good thing for you to aim at if you're a beginner, and I had a lot of fun writing it, and I really enjoyed making these systems that are supposed to do tiles and sprites draw little pixels, because they're not really designed to do that, and even if the graphics are limited, I felt a bit I felt like I'd achieved something doing it. I hope you've enjoyed watching. As always, please go to my website to download the source code for today's example, and if you can make anything better than I have out of it, then the best of luck to you. You're welcome to do so. Use it in whatever way you can. If you've liked this video, please hit the like button. YouTube recommends based on likes, so if you like the video, then other people might see it and they might like it as well. well. And also please subscribe, because making these videos takes a lot of time and it keeps my motivation up to keep making more of them. So that would help us both out. I get to feel like I'm doing something worthwhile. You get more videos, so everyone's happy. Anyway, thanks for watching today, and goodbye.